scanned PDFs look indexed until retrieval returns empty nonsense. I'll fix that in Python with Docling OCR fallback, so your RAG pipeline recovers real text, tables, and citations. This is the workflow you'll know how to run when we're done, which rescues text from scanned documents and retrieves relevant documents for a question. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Most teens hit scanned PDFs and think the index is broken. The file is there. The title shows up, but queries return unrelated or empty answers. That happens because OCR never happened or failed quietly. The retrieval system then matches on nothing, and you get hallucinations or empty results. Success looks like reliable matches to the actual content, not to metadata or file names. We fix that inside the ingestion step. We detect empty or low-quality text. We call an OCR fallback that extracts plain paragraphs, tables, and citation blocks. Then we reindex smaller searchable chunks, so the retriever has real material to score. At scale, this reduces empty retrievals dramatically and makes downstream generation grounded. Intuitively, think of each PDF as a set of text islands. If OCR missed a whole island, your search hits empty sea. We create a fallback lifeboat that pulls the island back into the index. For a tiny example, that means replacing an empty string with a recovered paragraph. For larger collections, it means adding table rows and reference items as separate sort chunks, so they can be matched precisely. We will build a small, practical pipeline that demonstrates the failure, calls Docling for OCR, pulls structured pieces, and runs a compact retriever to show the improvement. Nothing heavy. Plain Python requests, a few tokenizers, and simple scoring, so the behavior is obvious before you scale. First, let's show the failure case so we know what to fix. This snippet measures simple term overlap retrieval to expose how a scanned PDF that produced empty text fails during search. It sets docs to 2 items, where the first simulates a scanned file with no extracted text, and the second holds a short, usable sentence. The function overlap score converts each text and the query into lowercase word sets, then counts common terms. A scores list captures overlap for each document, and top I selects the best match by maximum score. Because the first document is empty, it cannot match the query, so the second item wins. The printed result confirms the empty text failure by pointing to the wrong source for scanned content. Next, we recover the text with an OCR fallback. This example performs an OCR fallback using Docling's REST API to recover text from a scanned PDF. It creates a requests.session named S, sets a base URL pointing to a local Docling service, and prepares in-memory PDF bytes. The code posts the file to the /v1 OCR endpoint and expects a JSON response containing a recovered text field. The variable OCR text captures the extracted content, and docs0 is updated so downstream retrieval can use the fixed text. If the service returns nothing, a reasonable default string demonstrates expected structure. The printed character count shows the recovered text length, confirming Docling produced indexable content. Then we validate by re-ranking with a simple BM25 style calculation. This code re-ranks the documents using a compact BM25 style calculation to validate the benefit of the OCR fix. It tokenizes each document with the function toke and builds a corpus D, then tokenizes the query queue. The dictionary DF counts in how many documents each query term appears, and IDF computes inverse document frequency with a smooth formula. The list scores sums per term weights based on IDF and term frequency in each document. Finally, top I selects the highest scoring document. If you add more documents, IDF will shift, rewarding rarer terms more strongly. The printed ranking shows the OCR corrected document now wins, demonstrating improved retrieval. After that, we pull structured cases like tables and citations to enlarge the index. This snippet enriches indexing by calling docling/v1 OCR/structured endpoint to extract tables and citations. It reuses the session S and base URL, posts the same in-memory PDF, and asks for tables and citations via the include parameter. The variable struct holds the JSON payload. Tables and cites lists pull their text fields, defaulting to empty strings when absent. The list chunks merges the base docs with structured items, ensuring tabular values and references are searchable. Increasing structured coverage typically boosts recall on table-heavy documents, but may add some noise. The printed count shows how many new searchable units were added to the corpus. Finally, we run a small retrieval over the augmented chunks to close the loop. This example executes a minimal retrieval over the OCR augmented chunks to simulate a small RAG pass. It picks C from chunks when available, otherwise falls back to docs. The function talk tokenizes each chunk. Q tokenizes the query, and D holds the tokenized corpus. The dictionaries DF and IDF compute simple document frequency and inverse document frequency weights, respectively. A per chunk score sums weighted matches, then top I selects the best chunk. Finally, preview captures a short slice of the retrieved text for a quick sanity check. The printed preview confirms your query now lands on OCR recovered content suitable for indexing. Taken together, this toy pipeline maps directly to a real ingestion service. In production, replace the small tokenizer with your standard one. Swap the simple scorer for a production BM25 or vector index, and call Docling asynchronously for batches. The core idea stays the same. Detect missing text, recover it, add structured chunks, then reindex. Recap: it is a practical OCR fallback, plus chunk-level reindexing that prevents empty retrievals. Use it when you have scanned PDFs, tables, or reference lists that standard extraction misses. Caveat: adding structured chunks can increase noise, so monitor precision while you improve recall. Next step: tune BM25, K1, and B on your corpus to trade recall and precision and measure retrieval quality. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.